Welcome to Lessons in Logic number 39, and let's do a little bit of practice with the basics of proofing. Now, this is going to be, well, I hope shorter than the last video, but also this is an introduction to the very basics. I had a student in my first logic class ever, Baylor University, the year 2008. I'm a grad student teaching, and this one student, whose name, of course, I won't mention, although I can still remember it, has a terrible time understanding these things. She's plenty intelligent. She just isn't used to thinking in this particular way. So I work up this really basic proofing worksheet to help her get the basics of proofing, and I think it really helped her. I've since put it on the internet somewhere, and now I'm going over it on this video. What we're doing here is looking at proofing very, very simply. A proof is a series of steps that show that the conclusion of an argument follows from its premises, and each step of a proof will apply a rule to one or more of the steps preceding it. And your initial premises are available as steps. So here is some practice using a rule, just one rule per proof, and then we'll look at some practice using multiple rules in another in a few moments. Okay, so here's an argument. If A, then G, J, if K, then A, if J, then K, therefore G. So how do we prove that G follows from all of this? Ah, yes, I'm now remembering that one thing I wanted to say in the last video that seemed kind of important that I forgot to say. We were looking at arguments and proving that the premises of an argument guaranteed the conclusion. And if you were thinking, yeah, but what are these arguments? The answer is, I don't know. We're looking at arguments that have already been symbolized in statement logic. Each of these capital letters stands for a statement. I don't know what the statement is. It doesn't matter at this point. Now, if we were going from the very beginning, we'd start with a cool argument, and we'd translate it into symbolic statement logic, and then we would do a proof on it. And in fact, what I should do, if my brain holds up, is go back and find that nice symbolized argument from Socrates and copy and paste it into my notes, and then look at the argument, the symbolization system, and then do a proof on the argument before we wrap up this section on proofing, which, by the way, I think is the end of the unit on deductive logic and the subunit on statement logic both. We might have a quick review video of statement logic, and then we'll do inductive logic for the remainder of the series. Anyway, if my brain holds up, I'll try to tie more of it together and give you some more practice with proofing and statement logic in general by finding that argument and looking at it again. We looked at it recently in an abbreviated truth table. We can do a proof on it too. It'll be awesome. So hope I remember that. But for now, let's not even care what arguments were symbolized here. We had arguments, we symbolized them. Someone symbolized them already. It's done. Here they are in symbolized form. We don't even care what the original argument is, because remember, we just care about whether the pattern of reasoning used in the argument is such that the premises guarantee the conclusion. So now let's confirm that that is indeed the case. So to complete this argument, to complete a proof on this argument, look for two preceding steps that fit the modus ponens pattern. So what fits the modus ponens pattern here? I recommend you pause the video while you think through it, if you're able to think through this, but can't think through it quite as quickly as I'm going to work with it. So right about now, pause. Whether you paused or not, let's proceed. Here are the steps that fit the modus ponens pattern. If P, then Q. P, therefore Q. That's the pattern that premises 4 and 2 fit. So again, we're trying to get to this conclusion, G. Those 3 dots mean therefore, if anyone's lost track of that information. We're trying to get to G here from these premises. And we can do it by using a modus ponens step. Once or twice, thrice, we'll see what happens. And we look for premises that fit the pattern. And this is what you do with every proof. Every step of every proof, you look for steps that fit the pattern. Premises or in some cases subconclusions, but subconclusions are still premises. So look for preceding steps. That's my generic way of saying premises or subconclusions you've already reached. Look for two preceding steps that fit the modus ponens pattern. Remember this dot, this therefore symbol G, this is not a preceding step. This is your goal. These are the steps. And we'll go back to the color coding, at least for the moment, that we used in the... And our bold red is the premises, and then our italicized blue is the goal we're reaching for here. Of course, it's trying to... It's messing up my formatting. It's still messing up my formatting. I don't know how to fix it right now. Okay, so the bold red plus the number 4 there are premises, and the therefore G is the conclusion that we're trying to get to it. So you want to find premises that fit this pattern. If P, then Q, P, therefore Q. And what fits the pattern? Premises 4 and 2. And from that, you get K. If J, then K, premise 4, J, premise 2, therefore K, by modus ponens on lines 4 and 2. Now, we probably won't go back to 4 or 2. Instead, we're just going to work with 5. So using, let's see, using 1, 3, and 5, just our odd numbers. Using these odd number steps, we should be able to get to G. And we're going to use modus ponens again, I think. So let's see what we can do with 1, 3, and 5. Using modus ponens. In other words, look for two steps that I've got highlighted here. If A, then G. If K, then A. K. Two steps that fit the modus ponens pattern. Modus ponens pattern is if P, then Q. P, therefore Q. What fits that pattern? Pause if necessary. Proceed. 3 and 5 fit that pattern. From if K, then A and K, we get A. And that's a modus ponens rule applied to 3 and 5. If K, then A, K, therefore A, 3 and 5. So now we've already used premises. We already used steps 4, 2, 3, 5. 2, 4, 3, 5. We've already used these. So probably all we need left to use is premise 1 and subconclusion 6, steps 1 and 6. So look for the steps that fit the pattern. There's only 2 steps left, and how convenient they fit the pattern. If P, then Q, P, therefore Q. And that gives us, if A, then G, A, that gives us G. Like modus ponens on 1 and 6. That's how proofing works. It's a series of steps where we apply a rule, and the rule is a pattern, and we apply it by just finding steps that fit the pattern and drawing what follows. These patterns in premises, this pattern in a premise will let you get this in a conclusion. Now, you're mainly interested in the final conclusion, the ultimate conclusion, the goal of the proof. But any subconclusion that gets you there is fine. And any step after the premises is a conclusion with respect to the premises. But once you have it, you can use it as a premise for whatever comes next. That's how subconclusions work. If P, then Q, P, therefore Q, use those use premises that fit that pattern to get to this conclusion. So now let's do the same sort of thing now in reverse, modus tollens pattern. Look for preceding steps that fit the modus tollens pattern. I really don't want to keep doing this, but maybe one last time I will make bold and red the premises we start off with, and italicized in blue the conclusion goal. So our premises are if A, then G, if G, then K, if K, then B, if B, then M, not M, therefore not A. So we can complete this proof by just looking for steps that fit the modus tollens pattern. What fits the modus tollens pattern? If P, then Q, not Q, therefore not P. So what fits these premises? If P, then Q, not Q. Well, it's statements 4 and 5 here. If B, then M, not M, therefore not B. So by applying the modus tollens rule to steps 4 and 5, we get step 6 tilde B. Now we do the same thing again. We've just used these. We're probably not going to use them again. So now look for any two preceding steps that I have highlighted. If A then G, if G then K, if K then B, tilde B. Premises 1, 2, 3, and then step 6. Look for any two steps that fit the modus tollens pattern. If P then Q, not Q, therefore P. Maybe I shouldn't say look for two preceding steps that fit the modus tollens pattern. Maybe I should be a little more specific. What we're looking for now is two preceding steps that fit the premise parts of the modus tollens pattern. If P then Q, not Q. So what fits that pattern? Well, it's if K then B, not B. So that gives us not K. If K then B, not B, so that's a modus tollens on lines 3 and 6. So now we've used premises 3, 4, 5, and 6. 3, 4, 5, and 6. We're probably not going to use them again. So now, premise 1, if A then G, premise 2, if G then K, and subconclusion, step number 7, not K. Look for two preceding steps among those that fit the premise parts of the modus tollens pattern. If P then Q, not Q. And then we're going to derive the not P that would follow. And clearly it's if G then K, not K, therefore G. That was a modus tollens on steps 2 and 7. Now I think our conclusion is going to follow with whatever is left. We've used steps 2, 3, 4, 5, 6, and 7. So now looking at premise 1 and step 8 there, steps 1 and 8, if A then G, not G, therefore, what would follow? Not A. Not A would follow. And that's our final conclusion, mission accomplished. Modus tollens on lines 1 and 8. We're done. That's how proofs work. Now let's do another one, and let's adjust this text so we can see it better. To complete each step of this proof, look for two preceding steps that fit the hypothetical syllogism pattern. Our premises, if A then B, if B then C, if C then D, if D then E. Our conclusion, if A then E. I think we'll do this in 2 or 3 steps. What fits the hypothetical syllogism pattern? If P then Q, if Q then R, therefore if P then R. So again, I'm not phrasing this quite precisely. My apologies to student back in 2008. I wish I had the sense to say this a little more precisely. You're actually looking for two preceding steps that fit the first parts, the hypothetical syllogism pattern, and then you're going to conclude the third part. So what fits if P then Q, if Q then R? Conclude from it the relevant if P then R. So this is the first natural place to start. Now you could actually start here or here. Everything would be fine, but let's start where it makes sense to start, where our brains conveniently work easily. If A then B, if B then C. That tells us if A then C, and that's by using the hypothetical syllogism rule on lines 1 and 2. And now we've used lines 1 and 2, we probably won't go back to them. So now, if C then D, if D then E, if A then C, look for a place to apply the same rule. If P then Q, if Q then R, therefore if P then R. And again, there's 2 places you could go, but I think it's probably simpler to start with, actually, I don't know what's simpler. My brain tells me start with the one you just used. If A then C, that's fine. You can do that. If A then C. And if C then D, therefore, if A then D by the hypothetical syllogism rule on steps 5 and 3. But I don't want to do it that way. I want to do C, if C then D, if D then E. So let's do that. So our first step of the proof was if A then B, if B then C, therefore if A then C by hypothetical syllogism. Our next step is if C then D, and if D then E, therefore if C then E by, again, hypothetical syllogism. So now we've used all 4 of our premises. So what we haven't used is these 2 things we derived from the premises, if A then C, And if A then C and if C then E. Well, you can probably already see what follows. If A then E is what follows by hypothetical syllogism on those two steps, which are steps 5 and 6. We're done. Yay! That's it. Proofing is that simple. Now this proof might be remarkably simple. Look for preceding steps that fit the disjunctive syllogism pattern. Our only premises are H or I in tilde I. The disjunctive syllogism pattern is P or Q, not P, therefore Q. Well, let's see. Do we have anything else? We don't. I should probably have another option here because the disjunctive syllogism pattern can also look like this. What on earth just happened to my keyboard? Hang on, let me make it stop giving me Greek letters. I don't know what happened, but I think it stopped giving me Greek letters. So that was really weird. I don't know what that was. So anyway, the disjunctive syllogism pattern can be either of these. Either P or Q, not P, therefore Q. Either P or Q, not Q, therefore P. So what fits that pattern? Well, both of these premises, obviously. H or I, not I, therefore H. Really, you just go straight to the conclusion here and say that it follows by the disjunctive syllogism rule on premises 1 and 2. That's it. Now this one might be also rather simple. The constructive dilemma rule is this: either P or Q, if P then R, if Q then S, therefore either R or S. Oh, I think I see what's going on here. Wherever I got this therefore symbol from, when I use it, I'm in a different font that uses a lot of Greek letters. So I wonder if I put it in Times New Roman, changes to a square. So I don't understand everything about computers. Anyway, here's the constructive dilemma pattern. I think our conclusion is going to follow by a simple one-step inference. If A then C, if B then D, and A or B, those are our premises. They fit the pattern perfectly, except the premises are not given in order. So the only thing here to be careful with is the ordering. This follows by constructive dilemma on lines 1, 2, and 3. Yes, but stated in the right order. Which line is the P or Q line? Give that one first. The P or Q line is 3, A or B. Which line is the if P then R line? That would be line 1. So the if Q then S line is line 2, if B then D. Either C or D, sorry, either A or B, if A then C, if B then D, either P or Q, if P then R, if Q then S. Well, I'm gonna have to go over that one more time because my brain is shutting down, freezing or something. Either A or B, if A then C, if B then D, therefore either C or D, if P, either P or Q, if P then R, if Q then S, therefore RS. Looks good to me. This is a good proof. It's that simple. So now, this might be another super simple one. Wow. Look for a step that fits the simplification pattern. P and Q, therefore P is the simplification pattern. So in this argument, we have an unnecessary premise that is just tripping us up. It's there to give us a chance to be confused. You can ignore it. How do you get from the premise A and B and the premise C to the conclusion A? Well, quite simply, you apply the simplification rule to line 1, and you ignore premise C. That's it. Now, another step in a proof, like simplification in reverse, is P, Q, therefore both P and Q. So how do you get that from an argument like premise 1, G, premise 2, V, conclusion we're aiming for, G and V? It's ridiculously simple. I think we go straight to our conclusion, G dot V. That's the conjunction rule on lines 1 and 2. That's it. Now, the addition rule lets us affirm from any statement that either that statement is true or some other statement is true. So from the statement Z, how do you get Z or J? Well, it's another simple one-step proof. By addition on line 1, you get Z, therefore Z or J. That's it. Proofing can be just that simple. And once again, all you're doing is looking for places to apply the patterns that are in the rules. Apply the first part of the pattern in the rule, the part before the therefore symbol, to a premise or premises, and then apply, and then draw the conclusion part that comes after, so that your cited premise, so your cited premise plus what you're drawing from it, your cited premises plus what you're drawing from them, fit the pattern of the rule. All we're doing is matching patterns. All right, practicing multiple rules. So let's do some more. Yay, to complete these steps, look for preceding steps that fit the hypothetical syllogism pattern and the constructive dilemma pattern. Now, if I haven't said this explicitly, let me say this explicitly. Not only should you, if you can do this, but can't quite do it as quickly as I can, as I talk through it myself, it might be good to pause the video and think through it. It also might be good to pause the video and write out the proof yourself, and then check your work against what I'm doing. Don't get too impatient. I mean, it depends on how much you need to learn this stuff and how well you need to know it, but you will know it much better by doing it for yourself. You might get plenty work doing it for yourself in your logic class at the university if that's who you are and what you're doing. But depending on who you are and what you're doing and how much you need to learn and how well you need to know it, for heaven's sake, don't just watch me do the proof. Pause the video, try it for yourself, and then check your work against what I do. Although there might be a few different strategies to get to the conclusion, which I will not go over in any detail here. To complete this argument, you should be able to apply the constructive dilemma pattern and the hypothetical syllogism pattern. Now, I'm going to follow my own advice here, or Dr. Beatty's advice originally, and work backwards. How am I going to get either C or F? Since I've already been warned that there's a constructive dilemma step somewhere in here, I'm probably going to get either C or F from these premises. And that means I'm going to need to get either B or E. Now, how am I going to get either B or E? Yes. I could get the B from the D. I could get the... Okay, goodness. I need C or F. Yeah, I didn't want to go into this kind of detail on this one, but we might as well. I need to get C or F. I can get C or F by some sort of constructive dilemma that allows me to get C or F from probably B or E. But how am I going to get either B or E? If I had an either B or E, then I could get either C or F from premises 2 and 4. How could I get either B or E? Well, I'm sure I'm going to have some, the B I'm trying to get is going to come from premise 1 in some way, and the E I'm trying to get is going to come from premise 3 in some way. And I should be drawing my arrows going the opposite direction. I'm laying out a pattern here for working backwards. So how am I going to get those A's and D's in premises 1 and 4? Well, obviously premise 5 is going to get me there. At this point, my errors have probably become useless. So at this point, actually, let me just stop annotating and just try something to see if it works. If A or D, sorry, either A or D as a premise, I can use that along with premises D or E. And the advice is look for preceding steps that fit the hypothetical syllogism pattern or the constructive dilemma pattern. So the constructive dilemma pattern will work here just fine. Either A or D. If A, then B. If D, then E. Pause and go back and put the pattern in front of you if you need to. The pattern is, constructive dilemma pattern is this. P or Q, if P then R, if R then S, therefore R or S. Okay, so A or D, if A then B, if D then E, that gives me either B or E. By constructive dilemma on 5, 1, and 3. So now how am I going to get from B or E to C or F? Well, it might be a simple case of let's see, B or E. Oh, it's another constructed dilemma. I'm not even using a hypothetical syllogism in this proof. Either B or E will give me C or F by constructed dilemma on line 6, 2, and 4, isn't it? Either B or E, if B then C, if E then F, therefore either C or F. So now I'm thinking, why did I even give myself any notes about hypothetical syllogism? Did I make any terrible mistake? Here's our proof. It's completed. It was a two-step constructed dilemma. Let's see if we can do something with hypothetical syllogisms, though. I think that's an alternative approach here. So I can use a hypothetical syllogism on these first two steps, and I think it'll work just fine. That'll give me if A then C. And then I can do a hypothetical syllogism on 3 and 4, giving me if D then F. And now probably I can ignore 1, 2, 3, and 4, and I just want to look at these 3 steps: A or D, if A then C, if D then F. So as I suspected, I can now go straight to the conclusion with a constructed dilemma on lines 5, 6, and 7. So you have to use a constructed dilemma rule to finish this proof. You can use only the constructed dilemma rule, or you can use the hypothetical syllogism rule. Either way is fine. All right, I want to do 2 more very quickly because I have to be somewhere in 6 minutes. To complete this proof, look for steps that fit the simplification pattern or the conjunction pattern. All right, I don't know what I'm doing yet, but I think this is going to be pretty simple. I think I'm going to simplify A and C out of each premise in which they appear and then combine them. So I think applying simplification to line 1 and then simplification to line 2 will give me A by itself and then C by itself, and then I apply conjunction to lines 3 and 4. To get the conclusion. Yeah, looks good to me. Looks like a solid proof. All right, to complete each step, look for preceding steps that fit the modus ponens pattern or the hypothetical syllogism pattern. Oh dear, this one's a longer one. Well, I've got 5 minutes to get somewhere. If A then B, A, modus ponens pattern, well, that's easy enough. I can get a B from that. I can use hypothetical syllogism to get C. So if I just look for somewhere I can start, these 2 premises will give me B, and the next premise will give me C, the next premise will give me D, next premise will give me E. Oh, well, this is actually very simple. I don't have to work backwards. I can work forwards. Working forwards can be very dangerous, as we already illustrated, I think, in the previous video. In this case, it's fine. I'm using it. We can get B from modus ponens on lines 1 and 2. And then using lines 3 and 4 in modus ponens again, we can get C. Not 3 and 4. Did I say 3 and 4? 3 and 7. We use lines 1 and 2 to get to 7, and then we use lines 3 and 7 to get to 8, which is C, and then we're going to use 4 and 8 to get to line 9, D. D follows from lines 4 and 8. So now I've got D in place, and that'll give me an E by modus ponens on line 5. And line 9. And now that I have E in place, I can go directly to the conclusion. F or G follows from lines 6 and 10 by modus ponens. And that's it. Proofing can be that simple. Now, I'm not going to go through this a different way since I just don't have time. And at this point, I hope those of you who need to know can figure it out. Briefly, take some of these things, take 1 and 2, or 3 and 4, or 4 and 5, or 5 and 6, and do a hypothetical syllogism on them before you use a modus ponens. This proof is simple enough in that if you start in one place where it's easy to start and work your way forward, it should work out okay. Another convenient thing about this proof is once you use a step, you should be able to ignore it. So if you were typing everything, once you use A and B, once you use 1 and 2 to get to B in number 7, you can totally scratch them out on your computer. And then once you use 3 and 7 to get to C here, you can scratch them out. So reusing premises should not be necessary. So if you need to, try to do the hypothetical syllogism part by yourself. I'm done. I have to go somewhere. And thanks for watching. And we'll probably introduce some new proofing rules or something cool like that in the next video. Bye.